In this video, we aim to provide a more detailed overview of the Joints tabs. While we have previously touched upon joints in earlier videos, this video will explore a more complex situation. Let's consider a scenario where we aim to create a custom robot. To achieve this, we can start by duplicating the station class and renaming it into Robot. Subsequently, we can open the new class in a 3D window. There are two primary methods for creating a robot. The first involves building it from scratch, a route we opt not to take. The more common approach is to utilize pre-existing graphics. In most cases, these graphics come in the form of either JT files or S3D files. JT is a format which is standardized from the ISO and is supported from many CAD systems. On the other hand, S3D is a plant simulation-specific format. The key distinction between JT and S3D files lies in their content. JT files solely contain graphics, necessitating subsequent kinematization. On the other hand, S3D files encompass a pre-kinematized graphical structure. This was demonstrated in the pick-and-place robot video, where we exchanged the graphics of the pick-and-place robot with those of a Comau robot stored as an S3D file. This pre-existing file already defined its joints, enabling us to utilize them for creating poses. In our scenario, we aim to replace the station with a JT file. You might wonder now why we didn't duplicate the pick-and-place robot and used it as a base to import the JT file. The rationale behind this decision is that at the station, we can precisely determine when each kinematization should be executed. Conversely, the pick-and-place robot autonomously determines the timing of its kinematizations. As demonstrated in the pick-and-place robots video, we could create robot arm animations to influence the kinematization. However, this approach is still limited and does not offer the same level of freedom as the station, which serves as a base. Therefore, if our objective is to have the new robot perform tasks beyond the capabilities of the pick-and-place robot, such as setting welding points on a part, it is more suitable to use a station whose graphic we replace. However, plant simulation inhibits the exchange of graphics of a material flow object for JT files. Consequently, we must first remove all graphics of the station. Subsequently, we can import the graphic from the JT file. We'll leave the settings in the upcoming dialog as they are and click on OK. If you wonder how we get this JT file, they are mostly publicly available to download from the manufacturer's website. If we right-click on the robot and open the Show Structure dialog, we'll observe that there are no joints. In order to create joints, it is important that we perceive the individual robot arms as separate graphic nodes in the Graphic Structure dialog. We will implement this in the following. When attempting to select a single joint, it becomes apparent that this is not possible due to the graphic being a monolithic entity. Therefore, we need to ungroup it. To do so, we right-click the robot and select Ungroup. After we did that, we are now able to select the graphics of the single joints. Now, we can commence the process of creating joints. We'll iterate through the graphics of the joints, starting with the graphics that shall be moved by the first joint which moves along the Z-axis. To achieve this, we need to select all graphics except the desired one. We can do this by using the shortcut Ctrl and A, and then deselecting the first graphic. Following that, we convert the group into an animatable object. Now, we need to position the crosshair so that it aligns with the 0 point of the joint. However, just the position of the Z-axis is crucial as the rotation occurs around the z-axis, which is determined by the x and y coordinates. Since the robot turns around its z-axis, we use it as the name. As visible in the upcoming dialog, the rotation axis is set to z, aligning with our requirements. We simply need to set the type of the joint to revolute and set a velocity of 10 degrees per second. Now, we can use the preview rotation dialog to get a preview of the rotation and confirm if the joint is moving correctly. If you accidentally set the position of the crosshair incorrectly, you can adjust the position over the rotation center group box. Now we open the group in a 3D window. We now repeat this step for the next joint. First, we select all graphics and deselect the next joint. Now we make an animatable object out of them. This time, the joint turns around the y-axis, so we name it y. Once more, we need to position the crosshair at the 0 point of the joint. In the upcoming dialog, we now need to set the rotation axis to y and the joint type to revolute joint. Then we again set the velocity to 10 degrees per second. Afterwards, we can once again preview the rotation. At this axis, we should utilize both the upper limit and lower limit, as the axis reaches them at a certain angle, which we can observe from the preview. You can define the upper limit in the same way. We skip it here for time purposes. Then we basically continue with the remaining axes of the graphic, however skip some of them as they are just repetition of the previous ones. At the fourth axis, we will encounter a challenge. So essentially our goal is to construct the robot's joints in a manner that aligns with the supported configurations of plant simulation. The supported configurations are available in the help section, as demonstrated in the video on the pick and place robot, but there's also a quicker way to access it. To illustrate this, we switch to our model frame. Here, we'll insert a pick and place robot and exchange its graphics with a Comau robot. Next, we'll access the robot's graphic structure dialog. Here, we observe that there is a z-axis, followed by two y-axes, and then another z-axis. However, upon revisiting the current joint of our robot, it becomes apparent that we naturally have a joint rotating around the x-axis. So, we would aim to incorporate an additional joint that revolves around the x-axis. The challenge lies in the fact that plant simulation would not support this configuration, as we can see in the graphic structure of the Comau robot. You might wonder why this adjustment is necessary. The reason lies in the intricate calculations happening in the background. Given the resource-intensive nature of these calculations, we cannot accommodate every conceivable configuration. However, by following the next steps, you can continue to create the joints of the robot successfully. Consequently, we need to make adjustments so that the joint rotates around the z-axis. To achieve this, we revisit the frame where the joint is located. Subsequently, we select the joints and choose Make Animatable Object in the dialog. We then label the joint as Z. The next step involves setting the crosshair precisely at the left bound of the current joint. At this point, the buttons on the right side are very helpful. The left button will set the corresponding coordinate to the left bound of the graphic, whereas the right button will set the coordinate to the right bound of the graphic. The middle button will center the coordinate. So for the x-axis, we can use the left button, and for the z-axis, we can use the center button. Then we press OK. We configure the joint type as Revolute and set the velocity to 10 degrees per second. After clicking OK, we open the joint in a new 3D window. Here, it becomes evident that the joint is not correctly positioned. It aligns along the x-axis. To rectify this, the initial step involves grouping all graphics. Subsequently, we access the transformation dialog. Here, we notice that the 0 point is at the center of the graphic. However, our preference is for the 0 point to be at the beginning of the graphic, allowing for a straightforward rotation around the y-axis. To achieve this adjustment, we first open the Graphic Structure dialog. Then we right-click the group and select Move Transformation to Graphic. Upon revisiting the Transformation tab, we notice that the transformation has been integrated into the graphic, placing the 0 point at the origin. Now we can then easily rotate the joint around the y-axis by -90 degrees. However, it is now necessary to navigate back to the previous joint. At this point, we need to rotate the joint once again around the y-axis by 90 degrees. By following these steps, we have successfully adjusted the configuration such that they align with the supported configurations. To continue with the next joints, we need to ungroup the joint again. For the sake of time, let's skip to the last joint. In the last joint, we once again perform a right-click and select Make Animatable Object. We assign Z as the name since the joint rotates around the Z-axis. Now we again need to position the crosshair at the 0 point of the joint. Then we click OK. In the upcoming dialog, we can leave the rotation axis as it is and select Revolute Joint as the joint type. Then we again set the velocity to 10 degrees per second. In the preview, we can observe that the joint moves accordingly. As demonstrated in recent videos, we now need to add an animation path in the MU Animation tab, as we want the parts to be animated on this joint. Clicking on the 3 dots allows us to select the default animation path. We can then show the animation path and edit its position. Setting the rotation axis to Y, we assign a rotation of 180 degrees. Next, we position the cone such that the part is animated in the middle of the joint. Since we want the parts to be animated on the last joint, we need to enter the last joint as the animation object. We can simply do this by right-clicking on the last joint and selecting Use as Animation Object. We now close the dialogues and switch to our model frame. Here we open the Show Graphic Structure dialog of the robot and expand all nodes. If we now iterate over the nodes, we will see that the joints are highlighted in the frame. Additionally, we can compare the structure to the structure of the Comau robot, and we'll see that they align with each other. Now, we need to open the Edit 3D Properties dialog of the robot and switch to the MU Animation tab. As you can see, the animation object is set already as wished, so we do not need to enter it manually here. Then we need to specify where the part should be picked by the robot. Therefore, we select Top as the MU side to attach. With this, now the robot is complete. If we now drop a part at the robot, we will see that it is animated on the last joint. As you can see, the states are also still visible. We can simply hide them in the Edit 3D Properties dialog. To show the robot in action, we now insert a source and a conveyor. We now start the simulation. As observed, the part is essentially animated on the robot and then advanced towards the conveyor. This is due to the robot being based on a station and just having a distinct graphic. Consequently, it functions like a station. If you're interested in exploring how this robot can be utilized, we recommend checking out our video on poses and pick-and-place operations for a more in-depth demonstration. However, we won't go in further detail at this point. Additionally, keep in mind that you can export the robot if you wish to use it further. We can do this by simply right-clicking on the class and selecting Save Object As. With this, our video on creating robot joints from an imported graphic is concluded.